Here's a very typical example. If I have a sequence like this, it's a sequence on a plane of points. If you look closely, you will realize it's just the points which are spiraling into the origin. But it's irrelevant. So I'd like to check that the d limit of this sequence is the origin. D limit of the sequence is the origin, meaning that the Euclidean, the limit with respect to the Euclidean metric of this sequence is the origin. So if I look back at the definition of the limit, I need to compute two metrics, or one metric. I need to compute the distance from my points to the origin in terms of my metric, g. Well, it's a Euclidean metric, that's the computation, right? If I take my components, I compute the way we compute the Euclidean distance to 0 point, to the origin. And if I benefit from the fact that the cos square plus sine square always return 1, it's of course just for the simplicity of the example, I chose such a sequence where the arithmetic is not so hard. You will end up that the distance from the x endpoint to the origin is exactly 1 on n, 1 on little n, on the index of your sequence. And now you can play with your epsilon and delta. You can say, whichever epsilon positive I fix, doesn't matter how small that epsilon would be, I can always find an index, capital N. And I can even provide the exact formula for the choice of such index, 1 on epsilon, such that after this place, as long as my little n index larger than this place, the distance of x to 0 will never be larger than epsilon. In the proof of the limit from the definition point of view, the main substance is providing this n. You have to convince everyone that the method of choosing this n for every epsilon works all the time. Well, here, that's my attempt to convince you. No matter how small the epsilon will be, I will always be able to choose an n like that, which will ensure this relation. Yeah. There's one problem, I mean, it's not a problem, but there's one deficiency of checking something by the definition, of course, because when you check that the sequence converges to some limit, by definition, you have to know this value of the limit in advance. Sometimes it may be a problem. But if you know it, then verifying by definition it's a good way. Most of the time, it's quite effective way to do things. There will be examples in the tutorial set where you will practice that. Well, that's the same thing. It just this line, this inequality, is just written in the language of balls. So B sub d, meaning that the ball with respect to the metric d, centered at the origin, radius epsilon. Yeah. So that's the sequence which is spiraling into the origin. The whole idea of the limit is that no matter how small you squeeze your ball around the origin, these blue circles, this is the Euclidean balls on two-dimensional place. Euclidean ball is simply a circle, or actually disk, I should be careful, disk. Circle plus the interior of that disk. As a matter of fact, just the interior, because ball is given by the strict inequality, so we don't take the boundary. So no matter how small you take a disk, your sequence eventually will enter the disk and will never leave after that. If you take a disk somewhere else, if you take it large enough, your sequence may be inside the disk for a while, but after a while it will leave. If you make a disk small enough, after a while it will leave and it will never come back. All what I just said in the plain English, it's all encoded in one single this epsilon delta definition. It is a skill which we're trying to teach. Which I'm trying to teach, and you're trying to learn here, how to see this connection between the plain English description and epsilon delta statements.